Hello students. In this video I'm going to justify the technique for the separation of variables for first order ordinary differential equations. If you haven't seen my video on the definition and some examples of separable equations, I recommend that you stop here and go back and check out that definition. Make sure you understand what it means to be a separable equation. You may even want to take a look at a video on how to solve a differential equation using the technique of separable equations, and come back and then try to follow along with this justification. Although I do offer an example in this video as alongside with the proof or verification, if you will. Okay, so remember, for this to be a separable equation, we have a function g that is written entirely in terms of the independent variable, and a function h which is written entirely in terms of the dependent variable, and we have a product of those two. So I'm going to divide both sides by h of y, and I'm assuming that h is non-zero. Okay, in this case, and then I have g of x on the right hand side. So I have 1 over h of y times dy dx. Okay, in the next step, what I'm going to do is I'm going to integrate both sides. With respect to x. So I'm going to integrate the left-hand side with respect to x and the right-hand side with respect to x. Now I'm going to rewrite this 1 over h of y as a p of y. It turns out it's not. This is just to keep it tidy. I could leave it as 1 over h of y, but that is just another way to write a function, let's say p of y, which happens to be equal to 1 over h of y. Okay. All right, so now notice I have p of y times a derivative. So if you recall, this almost looks like a chain rule has occurred here. Like as if I had a derivative, if I knew the antiderivative of this, then I'd be multiplying by the derivative of the argument. Okay, and that should remind you of a u substitution. And that is exactly what justifies the technique of separation of variables. Okay, so suppose that y is phi of x that satisfies this ODE. All right. Then what that would mean for the left-hand side is that if I take dy dx, I get phi prime of x, or you could, once again, as I said, as I alerted you to the fact that if y is equal to phi of x, then dy is equal to phi prime of x dx, and that was our substitution. So I haven't touched the right-hand side, but on the left-hand side, I've viewed this as a substitution. So I have p of y, which is really, you could view that as p of phi of x times phi prime of x dx. And since dy equals phi prime of x dx, then I'm just going to make that substitution here, and I would make the substitution that y equals phi of x if I had written this as a phi of x in here. Anyways, look on the left-hand side, and this is where the magic happens in terms of the technique of separation of variables, is I have an integral that is totally in terms of the dependent variable on the left-hand side, and an integral that is totally in terms of the independent variable. So if I knew the antiderivatives of p and g, then I could just write this as something as h of y and something that is capital H of y and capital G of x, where I stole the capital H from the fact that p of y is equal to 1 over h of y. And this fancy notation here, this just means that capital H, is the antiderivative of this function, because if you took the derivative of it, you would unravel it and you would get p back again. And if I took the derivative of the antiderivative, I would get the integrand g back again. And then I lumped the arbitrary constant here in terms of c. Okay, so that is the verification. Let me just show you what this looks like in terms of an actual differential equation. So imagine you had dy dx equals minus x times y. Well, beautiful. Okay, so that's the g of x is minus x and the h of y is y. So I divide both sides by y, and I have dy over y equals minus x dx. Now, that looks a little bit different than what I have here. So what I'm really doing is I'm going down here, and I've justified the fact that I could break up these differentials that way. And I'm not really breaking them up. What I'm really doing is this substitution. This is the undercurrent of being able to write dy over y equals minus x dx. All this here allows us to play fast and loose with these differentials, as long as you can justify what I've done here in these 1, 2, 3 steps. Okay, so now if we do that, this is what the technique looks like. I just integrate both sides, and here we go. I have the capital H is actually turns out in this case to be a natural log of the absolute value of y equals minus 1/2 x squared plus c. At this point, you're done with the technique of separation of variables. If you wanted to solve for y at this point, you just are using algebraic properties, and you would do something like this. You would exponentiate both sides. Um, you'd realize that e to the c is an arbitrary constant, so you can write that as c. Remember that if you have things with powers with the same base, you add their exponents. So that means if I have something e to a sum, I could break it up as a product of exponentials. Um, and then e to the natural log gives me y again. I could put absolute value bars around here, or I could just view this as this is always positive because c is equal to e to the c, so that's always a positive number. And that would be the solution to my ordinary differential equation. And I've exploited that technique. So in practice, we break up these differentials, but in theory, that is justified because of this step here, where I assumed that I can write the solution as y equals phi of x and then use the substitution method. So that's the foundations of the technique of separation of variables. Good luck.